what is going to happen. What are the major cases of particles moving in magnetic fields? We have three main cases. As you can, if you just analyze it, doesn't matter if you look at this expression of this expression, you can actually understand what is going to happen. We have three major cases. The first one, I think, is the easiest one, is actually when the velocity of the particle is actually parallel to the magnetic field. In this case, if these two vectors are parallel, right, that means that we have that this sign here is going to be like sine of 0 degree 0, so that means you have no force, so you have no influence from the magnetic field on the motion of this particle, and then nothing is going to be observed. Would be something like this. Let's say you have a particle here like moving this way, and the particle would be the motion. The particle would keep its own movement without being influenced by any force generated by the magnetic field. So that is this case. That is the first and most easier case. Remember, since this vector product here, I use this a simpler version of the expression, right? But we know that this vector product here is going to be 0, so there is no force acting on the particle. Okay, and then let's see another case. Let's imagine now that you have what is going to happen if you have a particle that actually when enters the magnetic field, the angle between the velocity of this particle and the magnetic field is 90 degrees. So what is going to happen is actually, first of all, we have a force. A force is going to act on the particle, and for example, in this case here that I'm considering like a negative particle, right, with this velocity pointing in that direction. Oh, this was supposed to be I had here. Okay, if you do this product here, what you can see, there's actually, we have the magnetic force like pointing in the positive direction of the y-axis. Let's see the simulation. Maybe checking the simulation is easier to understand what is going on here. So I have this simulation from developed by Tom Walsh, so you guys can understand. So here, guys, we have a particle here in orange, and the particle is moving in the positive direction of the x-axis. We have the magnetic field in green pointing in the positive direction of the z-axis. And let's see what is going to happen with a negative charge entering this magnetic field. As we saw before, using the right hand rule or the vector product, we see that we have like a magnetic force like pointing in the positive direction of the y-axis that is represented in green here in our drawing, right? Let's see what is going to happen here. As you can see, the particle is going to circulate, is going to acquire like a circular motion, is going to describe like a circular motion around the z-axis. If you see from above, what you see, if the particle is actually entering with a velocity that has 90 degrees in relation to the magnetic field, this particle is going to rotate around the z-axis. Very interesting result. Let's pause here and let's remember, we saw this also in this experiment, right? What we can see in this experiment here, it was exactly the same thing. If you have a perfect circular motion here. Let's see. You can see here perfect circular motion of those particles. So let's go back here and let's try to actually formally try to evaluate this circular motion. What I mean with that, well, we know everything about circular motion. We know all the expressions for the magnetic field and so on. So let's try to quantify that using our mathematical expressions. Right, so we have the magnetic force here is going to be, I put in purple, so let's keep the purple here. So the magnetic force is going to be FB. Is going to be Q V B, and in the J direction, J is blue. No, here is blue. Okay, and of course this force here is actually, since the particle is experiencing a circular motion, this is actually balancing or supplying the centripetal force. So that means that we can actually equate this. They should be balancing each other. So that means we have the centripetal force should be equals to the magnetic force generated in the particle. This one, we know the expression for this one. This is m v squared over r, and the magnetic force that we learned today, where we are familiar with it, is qvb. All right, we can simplify. Actually, what I'm interested here is in find one expression for the radius of the circular motion, right? I think this is the most basic information. Is one of the first I want to know. What is the radius of the circular motion? Remember, guys, since we know that this is circular motion, we are trying to find relevant, significant variables that describe the circular motion, and we know many of them, right? You know that it's going to be the radius, the angular frequency, the frequency of motion, and what else we have? Yeah, and the period. So those two are actually equivalent. So we are actually interested in finding expressions for this one, and the radius is very easy. We just have to balance these two forces here, so we can find then that the radius for this circular trajectory is going to be m times v, and then divided by, let's try to make as much perfect as possible. I put like big R, no, let's use like small r. Let's keep my notation. This is R, this is QB divided by QB. Okay, you have one expression for the radius. Guys, that means that this radius is actually proportional, directly proportional to the velocity, inversely proportional to the magnitude of the magnetic field. We can play using the simulation to see how changing those variables here are going to change, are going to affect the radius of the trajectory. But it's not the point here. So we can actually, from here, we can calculate the velocity, because we know that the velocity in the circular motion is going to be 2 pi r over t. So the linear velocity is like this, divided by the period of the circular motion. We can substitute here all these guys that we have, right? We can actually grab this expression here that I just calculated. Let's call this 1. I can substitute here, and since I can calculate the period here is going to be 2 pi r divided by v. I can actually substitute here, and I have that the period is going to be 2 pi m divided by qb. QB, and of course, because the frequency is the inverse of the period, right? We can actually just directly write here. Since, okay, let's put here just for the nostalgic feeling of high school. This is the inverse, so this is going to be QB over divided by 2 pi m. So this one is important. We're almost there, almost characterizing the whole circular motion. For this particular case, let me highlight here these results. Good, okay. Dun, dun, dun. And the last thing that I'm going to calculate is going to be the angular frequency omega. This is going to be easy also because we know from high school. Wow, not so good. Omega is equals 2 pi f, or 2 pi over the period. We can calculate the angular actually frequency like this, and we can actually find the angular frequency for this case is going to be QB divided by m, and we can play this actually this in our simulator here, or simulator. You can play to see what is going to happen, how those changes in the charge, in the mass, are in the velocity, right, is going to actually affect here. Even the, I don't, oh man, oh yeah, you can change the field too. See, you can change the field, you can change the mass to see how it's going to affect the circular motion, and you can change the charge. Oh my god, positive. See how it's affecting. But we have the analytical expressions to calculate precisely how it's going to affect. To calculate, not precise, to calculate quantitatively. So this is qualitative analysis, right? But we have those for the quantitative analysis. Okay, and last case. So I studied two cases here, guys. This case here, and the last one we are kind of interested. Uh, so this was case one. That was the simplest. This was case two. Very interesting case. We have many applications in this for this in industry and so on. And finally, let's analyze another case. What is going to happen if now the velocity has like a general direction? For example, in my case here, let's say that the velocity has one component in the y direction and another component in the y direction. Oh, in this case, because I'm going to use our simulator here, in the z direction. Let's go and see the simulation first. Let's put here one velocity. Let's say it doesn't matter, small, 0.1 maybe meters per second in that direction. Let's see in 3D. Let's reset here. Okay, let's remove the magnetic field. Keep in mind the magnetic field is pointing upwards in here. Okay, and let's see what happens with the particle. Look, whoa! The particle now is describing a helical trajectory. The component in the x-axis is going to still generating a force that is pointing in the direction of the z-axis, right? So that means that the charge is still like rotating right around the z-axis, but you have one component of the velocity that is actually parallel to the z-axis, and this one is making the particle to start spiraling. I think those guys use spiraling, I don't know, for tricks in the when you're piloting an airplane or something. For in physics we say helical, because since we actually have like one equation to describe this kind of motion. So let's go back here, guys. So if you do this and look and you calculate, since remember, let's put some colors here just to, so this is in the I direction, this in the k hat, I hat and k hat direction, and we have here the B, my vector B from my experiment there, right? This not my experiment, my simulation there is actually B, and is in the k direction, k hat. Ta-ta. When you operate, when you perform this vector product here between V and B, what I'm going to have Vx B, and this is I hat vector product with k hat plus the other component there, V z sub z times B, and this is going to be in the k hat direction. So this is the vector product between those two vectors. We can recall, we can come back here and grab our practical mnemonic here to remember the vector product. Let's go. Where is it? Here. Okay, can put here. Let's put this here. So this one is going to be 0. This one, this one is 0, and this I time vector product. Oh man. Sorry for the. Okay, guys. So this one is going to be 0. This one is going to be j, minus j actually. Ik, oh no, ik minus j. So that's the point. If you see here, so this is going to be negative, but since the particle, right, is 1 electron for this case, for our simulation here, so that means that the force is still like pointing inwards here, not outwards. And but actually the force still acts radially like before, right, like in the case 2, but now we have it's still so this component here is going to act radially and is going to actually affect, is going to change the direction of the vector v on the xy plane. So this one is still affecting the xy plane, and this one doesn't affect anything. So since this velocity here is constant, right, in the z direction, that means that this is going to give you this helical trajectory that we observe here, like this. Beautiful, beautiful, beautiful. Okay, I think that for that part is this. So let's move to the next part. Let's go back here to our problems.